Hey gang, and welcome to another exciting episode of Biology Online. And I'm going to take a moment and I'm going to review how to do a dihybrid cross. So I've already kind of got a Punnett square set up, and I've already assigned a genotype for both traits to both parents. And there's a reason why I'm going to choose this particular genotype. And it's because it's going to give us the greatest possible combination of gametes. So this is, I guess you could say, it's the most complicated one, or the hardest one to do, I guess you could say. It's not really difficult at all, but compared to some of the other gene options, this will give us the greatest variation of offspring, so it'll give us the biggest Punnett square that we can have with the dihybrid cross. But to make it easy, I've given both parents the same genotype. So once we figure out what gamete combinations one parent can give, it will be the same for the other. Just one will be egg, the other one will be sperm. So to start off, the genotype combination that I'm going to give you heterozygous, meaning one big, one little, for both traits. So big A, little a, big B, little b. And you can choose whatever letter you prefer. Again, use letters that are easily distinguishable between their uppercase and lowercase, so that way when you're in a hurry and you're writing them, they don't look the same. Like big C, little c, when you're in a hurry, they look the same. But big A, little a looks very different. Big B, little b, very different. And there's several letters that are good examples. A's and B's are one of those. So here we go. Let's just kind of jump into and see what this is going to look like here in a sec. So here is our genotype. Whenever we start to do this, the first thing I want to do is underline each trait to let me know that this is one trait, this is the separate trait. How to know their traits? Well, the A's go together and the B's go together. That's two separate traits. Okay? Whatever trait you're talking about, it's two separate traits, so I underline them to let know they're separate. The next thing I do is I have to remember that these letters represent chromosomes, and whenever the adult produces egg or produces sperm, they have to go through meiosis in order to produce that egg or sperm. And when we do that, we go from diploid to haploid. So the number of chromosome gets cut in half. So I draw a line between the big A and the little a and the big B and the little b to let me know I should not have a big A and a little a in any of the resulting sperm or egg. Because of meiosis, remember, we separate those apart. And the same thing with the B's. They have to be separate from each other. So I should have one of the A's and one of the B's in each sperm or egg. Think of it like this. There are 4 letters up here, big A, big B, little b. That's 4 chromosomes. That's our diploid number. The resulting sperm should have haploid. It should only have 2 chromosomes. It's got to be one of the A's and one of the B's. But it can't be both A's, it can't be both B's. It's got to be one from each. So the easiest way to do this is I kind of do this using a method called the FOIL method. Now you probably remember this from algebra when you're doing, I think it's quadratic equations. You do the FOIL method. And it stands for first, outer, inner, last. This method only really works for dihybrid crosses, but it still works pretty well just to help us keep up with things. So if we did the first letter in each group, we would have a big A, right, and a big B. That's the first one from each group, right? First one for each trait. Then you go the O for outer. What are the outer 2 letters? Well, you have big A again, and then we have little b on the outside, right? The I stands for inner, so what are the inner 2 letters? We have little a, and big B is also on the inside. And then the L stands for last. What are the last 2 letters in each trait? Well, we have little a, right, and we have little b. Let's see, again, 4 chromosomes up here. They go through meiosis. There should be 2 in each resulting sperm or egg. So this one's got 2, that one's got 2, that one's got 2, that one's got 2. I don't have 2 A's here, so I'm good. I don't have 2 B's in any of them. I have 1 from each. Each one of these is a resulting sperm or egg. This has the correct number of chromosomes, so when the sperm combines back together with an egg, they'll add their chromosomes together to get back up to diploid. So yay. I'll just make these sperm because I like drawing the tail. All right, so because both parents have the same genotype, I could work this out again for the female, but she would have the same combination that she can give. So we don't need to do it again. We're just going to take these and write them over here. So for the male, I'll put the big A, big B, big A, little b. Wonderful handwriting, right? Little a, big B, and then little a, little b. So the female will have the exact same genotype. I'm just going to write hers across the top. So we have a big A, big B. We have big A, little b. We have little a, big B. And then we have little a, little b. All right, so again, we take what's on top and we drop it down, being sure to write the dominant letter for each trait first for that trait, and what's on the side comes across as well. So we have big A for this block. That's what it end up here. And then we have big B, big B. So one of the kids could end up with this genetic combination. The next one we have big A from the top and big A from the side. Now here we have a little b, but again, on this side we have a big B. So I'm going to write the big B first, and then I'll write the little b second. Right? So over here we have big A with a little a, and then big B, big B. And then we have big A, little a, big B from the side, and little b from up top. I'm not going to fill the whole thing in for you, but just to kind of give you an idea, this is essentially how you'd go through and fill in each of the blocks. Just what's on the top, bring it down, what's on the side, bring it over, put the A's together, put the B's together, make sure that the dominant, if there is a dominant one, then make sure it's before the recessive for that trait. So big B goes in front of a little b, big A goes in front of little a. And essentially, you fill in the Punnett square in this fashion. What about trihybrid crosses? So let's do one real quick. Let's do a trihybrid cross. All right, I'm not going to worry about filling in the Punnett square because that would take some time. We kind of have the idea it's going to follow a similar pattern as we did with the dihybrid cross, but because it's a trihybrid, the full method doesn't work. So let's kind of go through a slightly different method that we can use for figuring out, well, you know, which one of these is, what possible gamete combinations can an individual for a trihybrid cross give. All right. So again, the first thing is we underline each trait. Underline the A's, underline the B's, underline the R's. Then we divide the two A's, because remember this represents meiosis. The chromosome number is going to get cut in half to make the sperm and egg, right? Each one of these letters represents a chromosome, so there's 1, 2, 3, 4, 5, 6 chromosomes. So that's going to be our diploid number. When we make the egg or sperm, it's going to be haploid, so half of that. So we're going to go from 6 down to 3. So it's a good way to double check to make sure each of your possible gamete genetic combination has the right number of chromosomes, right? So full doesn't really work for this, but the easiest way to do this is I think of this like a clock. Where on a clock you have hours, minutes, and seconds. The seconds are the last one in the order, and they constantly change. They change more frequently, right? The minutes change a little less frequently, and the hours change the least. So I'm going to start off with big A, then I'll have big B, and I'm going to have big R, right? So this kind of represents the hours, minutes, and seconds. So when that's one possible combination, all dominant, right? One letter from each one. Again, we shouldn't have two A's together. We shouldn't have two B's or two R's, right? Because we're cutting the number in half to make gametes. So the next one, the A is going to stay the same because that kind of like the hours. It doesn't change that often, right? The minutes will change more often, but the R's are actually going to change almost every single time. So big A, big B, big R, big A, big B, little r, right? So, cool. What would the next possible combination be? Again, hours change the least, so I'm still going to use a big A, but next comes the minutes. I haven't done any little b's yet. There's a little b, the seconds change back, so it's going to be a big R. What do you think is going to come next? Big A again, little b, because we haven't done the minutes yet, seconds yet, we haven't done the little r's. So big A, big B, little r. So if you notice, the r's change every time, the b's change every other time. What's the only thing we haven't changed yet? The only letter that's up here that hasn't been represented at all, and that's going to be the little a's, right? And so here's here's it is written with the little a's in front. If you look at this and you go through and you think there's a very systematic way of doing this, changing the last one more often, changing this one first, then changing that one in the middle, and then changing this one last, we end up with a very systematic written out structure for the different gametes that can be produced. So with this heterozygous for all traits for this trihybrid cross, there are 8 different possible combinations of gametes that can be produced by both parents. So like the female can produce 8, the male can produce 8. So the Punnett square for this would be 8 across the top and 8 across the side. So it's an 8 by 8. So that would be 64 squares to have to go through and fill in. And you're thinking, wow, that's a lot. Yeah, well, this is only 3 traits. Your body does this with thousands, if not tens of thousands of traits. So there's a huge set of possibilities for every offspring whenever something reproduces sexually. And that's great. We need that genetic variation in the offspring because, well, different variations of offspring gives different survival rates to each offspring, depending on the environment that they're in. Some of those variations may work better in that particular environment, others may not. Natural selection tends to remove the variations, the genes that don't work well in that situation, and it promotes the genes that do. And that's how we that's the process of evolution, and it all starts kind of here. So this is where it all starts. But anyway, this is how you would simply break down this is how you'd solve for a dihybrid cross and also for a trihybrid cross. Hope this was helpful.